Welcome everyone to sixth lecture for CS329A. We'll today cover train time scaling or scaling RL. So far we have gone through several topics related to test time scaling, feedback using tools and code, and then also robust verification. Today we will see how we can close the loop to improve the models even further. Okay, so today's lecture we will actually cover three papers. The first paper will cover how can you boost the reasoning capabilities of the models with putting rationales in problems. This paper is called STAR. It was actually done by an author at Stanford. The second paper we will cover is DeepSeekMath, which talks about mathematical reasoning and how that can be boosted in language models. And then the third paper is more focused on reinforcement learning and how when you have to do reasoning with long reasoning chains, how can you stabilize that kind of reinforcement learning algorithms? So to ground a lot of to motivate a lot of the papers that we'll present today, if you look at a benchmark called AIME, so AIME is a benchmark which is on mathematical problems, which tests for mathematical reasoning. It's very similar to say, it's more complex mathematical reasoning problems than say what was in a math benchmarks. We used math benchmarks earlier this year, and then that one is already saturated and contaminated in most of the models. Basically, most of the models have been trained on it, so we had to change the benchmark. So this is AIME 2024 and AIME 2025, the benchmark that you use in homework 1 is a recent benchmark that has mathematical reasoning problems. And if you were to evaluate GPT 3.5, which is a 175 billion parameter model, you will get, or that's what it's believed to be, you'll get almost 5% accuracy. But if you were to take DeepSeekMath, which was using train time scaling on a 7B model, it gets 51.7% accuracy. And with additional tricks, it's able to even get 60% accuracy. And if you apply the third paper that I will talk about called DAPO on the Qwen32B model, you are able to get 50% accuracy. So in the prior work or in the first lecture, we were saying that as we scale the number of parameters in the model, that's when the model capabilities go up, the model accuracy on benchmarks go up. But what we are seeing in this particular slide is that you can achieve a pretty high performance on reasoning benchmarks with smaller models. So how did these smaller models get really performant? How did they get really high accuracy? So that's something that we will kind of explore in this particular lecture. And some of the tricks that are being used to achieve this are called train time scaling. So typically, if you try to do reinforcement learning on reasoning, it will not work well. And a lot of the times, the reason it doesn't work well is because the implementation details are hard to get right. So the key insights that we will study today are that if you have a model, earlier you were just training it on internet. So pre-training, the technique of model training was training the model on internet. If you allow the model to learn from their own outputs, by filtering cleverly, you can improve the models even further. Hence, the class is called Self-Improving AI Agents class. And then the amount of compute you invest in training the model on its own outputs can substitute for the model parameters. This also parallels some of the earlier efforts where the amount of compute used in training smaller models, if you could increase the amount of data, has been shown to help improve certain benchmarks. And then the third point is that when you're doing reinforcement learning as opposed to supervised learning, you have to really be careful about details of the implementation, because as you scale up those algorithms, the small fixes can be extremely important. So the three paradigms that I'm talking about here are pre-training, which is basically you're training the model on internet, that we have talked about in the first lecture, and we're not covering that much in detail. And then the next technique would be that fine-tuning, which is how you get your chatbots, where you're basically perhaps fine-tuning or doing reinforcement learning with human feedback or RLAIF on preference data from humans. And then the test time scaling, which was some of the techniques that were covered in previous lectures, those are more techniques where you're basically doing some sort of, say, majority voting or inference time sampling and then combining the outputs from the how you sample from the model. For example, in homework 1, you are evaluating majority voting, then you are evaluating some other techniques that combine and evaluate the errors in what the model is producing and then using that to improve the model. So test time scaling is mostly inference-based techniques. Now, if you take what the model output, filter after applying this test time scaling and then use that to fine-tune further, that's roughly what train time scaling is. So if you take nothing away from this entire lecture, but you just remember this loop, then you kind of have learned the basics of what train time scaling does. Questions?
How do you know like what is like the good balance to distribute your compute into train time scaling versus test time scaling? Like, is there like a flat like ROI curve that you reach at a certain point after investing in train time? I mean,
great question. Let's hold that question until the third paper. Cool. But definitely ask that question again. So roughly, what happened last year was that the reasoning model, this is a graph on O1 and O1's accuracy on AIME. It's pass at 1 accuracy on the y-axis, and then the amount of compute on x-axis and train time is shown on the x-axis on left graph, and test time compute is shown on the x-axis on the right-hand plot. So what is happening here is that as we are increasing the test time compute that we have already seen, the pass at 1 accuracy should go up. So this is a log linear plot, and so more inference time compute, better pass at 1 accuracy. But what they're also showing is that if you can increase the train time compute, then you can also improve pass at 1 accuracy. So what O1 showed for AIME benchmark was that by increasing both the train time compute and the test time compute, you are able to improve the accuracy on the benchmark. And so it allows you for basically a circular loop where like you can generate model outputs and then feed them back to improve the model on this particular benchmark. Now, why does this work? So math is a domain in which there is verifiability. So we had a whole lecture on robust verification. So you have the ability to know which outputs are correct and which ones are not correct. So you have some ability to actually choose the correct outputs that can then feed into train time scaling. So this works better in domains where there is verifiability. So typically, why does reasoning start to help? So this is a repeat of some of the slides, but I think it's very important to remind folks that all the reasoning models in O-Series or Gemini Flash Thinking or the equivalents in other frontier labs, basically reasoning allows us to solve for difficult problems, because when you're solving a difficult problem, you will not just spit out the output. Even in chain of thought in math problems, when you were asking the model to think step by step, it allowed a certain amount of tokens to be dedicated to spelling out the reasoning in step-by-step process. So thinking models use a chain of thought where when they're attempting to solve the problem, and what these tokens might get dedicated to is you will see patterns like problem analysis, where they might actually try to understand what the problem is describing. Task decomposition, I'll show you an example of this, but where they try to decompose the task into subtasks. Self-evaluation, they might actually try to look at the answer and then be like, okay, this is not looking correct. So they might actually choose to backtrack and recognize their own mistakes and then backtrack to a previous step where they redo the problem. And they might try some kind of different approaches. So it's like a somewhat parallel search where they might actually try multiple approaches at the same time instead of if the current one is not leading to a solution. So it needs to have some sense of whether it's the correct solution or not. So here are some examples from earlier version of the model in O1 series. So here the user is requesting a bash script where it wants to understand. So it's requesting a bash script that will represent a string with this format and print out the transpose in the same format. So it's taking a matrix and printing the transpose. And what you see in the output is that the model first tries to understand what the user is asking in terms of input and output formats before it tries to solve the problem. So that's more of a problem analysis kind of pattern. Another example for the same problem you see is that it tries to decompose the problem. So it will actually, once it understood the problem, it's saying that the approach should involve, maybe I should parse the input string, then build the matrix, transpose the matrix, and then output the matrix in the same format. So it's breaking it into multiple steps. While for this particular problem, this might be an overkill, but in more complex problems, this might be a better way to solve the problem because you've decomposed the problem into smaller steps. And then self-correction. So this is a different problem from chemistry where it's asking pH of some solution on a chemical, and the model starts to compute the pH value, but then it suddenly has this notion of, wait, the correct formula is different, so it basically goes and changes the formula that it was going to use. So even though it's pulling from the knowledge that the model already has, it's actually correcting itself, so it has the capability of self-correction. And how does this help the model? So as I was trying to explain before, in domains where you have verification, like computer programming or data analysis or mathematical calculation, the win rate over GPT-4o, which was not a thinking model, you'll see that it's greater than 50%. So certain domains benefit way more from this train time scaling kind of techniques, as opposed to if you look at personal writing or editing text, there's not as much improvement in terms of win rate. Win rate means like if you were to give humans output from GPT-4o versus thinking models, personal writing and editing text may not see as much gains, but domains which have the ability to verify and close the loop see more gains. Questions?
Go back to 12 pages ago was to compute like the plot. Well, yeah, if you look at the very right, so the left is a train time compared to the time is test time compute. But minus 10 to 0 times. It seems the test time performance is better than the train time performance. Like on the right, it seems it's very close to 80 already, but on the left, that is low. So in this specific case, the test time performance actually is better than the training time performance.
So in this particular plot, it does look like that.
But that's kind of...
There is no intuition around these things as to like one should be better than the other, I think. I mean, you have to, this is one instantiation of where things were, and I just wanted to show you the curve.
Typically, you see the test time performance better than the training time performance. That means something suspicious going on.
Something suspicious going on, okay. I copied the plot, so their graphs are not always right, as you might know from their latest release. Okay, so let's go back to the fundamentals, right? So what is it that we're trying to answer? I think the fundamental question we're trying to answer is that in test time compute, you can basically, if you go back to this plot, test time compute is very cheap for someone to put, because you've trained a model, and then you can go and do multiple inferences, and if one of the answers is correct and you have a good verifier on your end, then you can basically scale compute infinitely. In fact, I think next Friday, I'll go through some papers, including AlphaCode, for example, and what you'll find there is that if you can basically make your search infinite in some ways, then in test time, you basically have a solution that will be correct, because from test time scaling, we do know that there is a correct solution if you repeatedly sample, right? Train time scaling, the challenge will be that you have to scale it correctly, which we'll cover in this lecture. And then the second bit is that there's a certain amount of this closed feedback loop has to have enough successes for the train time scaling to work well. So you will see that in the papers that I'll present now.
So that plot is actually different than like in the traditional machine learning to compare the training time performance and test time performance, because that plot is showing it's actually more efficient if you put the compute into the test, because when test time compute increases, the accuracy increases faster than time. Like given the same compute, if you apply that to test, it's actually you have better performance.
So there is a caveat to what you're saying. Test time compute works well in benchmarks where the verifiability is robust. Otherwise, you do need to get the model to start to reason better, because you need some verification loops. So both serve their, I mean, this is something we'll discuss in the lecture, but both serve their goals. So like if you prefetch what I'll present by the end of the lecture, when you look at a pre-trained model, what it is good at is it has certain level of capability in, say, solving mathematical problems and solving reasoning problems and reasoning about finance or legal or whatever, based on whatever domains it has seen already data in. But then in inference time, you're basically getting it to reason over multiple of these traces and then picking one. If you know and have a good way to verify the solutions, then you can like pick one of the solutions. That's like saying I'm going to throw spaghetti at the wall and I know where it should land. Otherwise, with train time scaling, you can teach the model and boost the pass-it one accuracy so that there's more likelihood that it will emit the correct output. But you still need verification of the loop. More questions? Yes.
So when you're fine-tuning the model to be able to solve difficult problems better, does it have any regression on solving simpler problems? And if so, how do you prevent that?
That one also needs to be. Let's keep those questions. I like all the questions, but we need to get to the first paper, and then we can ask that one. Typically, there shouldn't be a regression on solving easy problems if you're solving difficult problems, unless you basically go into like reasoning chains that are completely broken in some ways, so repetitive reasoning chains, which is called as overthinking. So let's cover the first paper first, where we are basically teaching the model how to reason. So we are boosting the reasoning capability of the model with reasoning chains. So let's take a look at how we can do that. So we already covered this earlier, and we showed this in the first lecture. So chain of thought in large language models provides both interpretability, and if you ask the model to show its work step by step, then boosts mathematical reasoning, and we saw several benchmarks, common sense reasoning, and so on. So we want to basically get the model to have strong step-by-step reasoning capabilities along solving any problem. What is challenging with existing approaches, if you were to like try to get this in existing approaches, so no internet scale data has really reasoning steps most of the time. There are very few internet sources that have the large scale reasoning steps. And then if you try to manually annotate reasoning steps, that's very expensive because you literally need humans to annotate those reasoning steps. And if you try to automate this process of like generating reasoning based on known solution patterns, then that also works only in very, very specific domains. And then if you try to few shot prompting means like if you give it a few examples of like, here is a problem, here is a reasoning chain, here is an answer, then that still underperforms models that can be fine-tuned on just larger data sets. So basically, small amount of reasoning examples don't quite cut it, and you can just have a larger data set without reasoning chains. So the key insight that STAR has is very simple. First thing, so this is a very simple example. Like it will start with a small number of examples that as reasoning steps. It will generate solutions. So say 10K problems. 10K is a representative number, and then it will only keep the ones that have correct answers. But it will generate these problems with rationale. And it can fine-tune on those, and it can repeat. So it can repeat this loop. So what's new here compared to what we were doing in test time scaling is it's only keeping the ones that have correct answers. Now, why did it not produce correct answers on the other ones, and what can we do with those particular set of examples? So that's the other interesting bit. So in certain problems where it could not solve the problem, the model got stuck. So what we want to do is we basically, if we just fine-tune on the correct examples, the model is not able to learn how to solve new problems. Let me cover this slide and then we can come back. So there's basically no signal. So what we do is we give the model the answer and ask it to explain backwards. So it's almost like I have this question, I asked the model to produce the answer, but now the model did not produce the correct answer. So I give the model the answer and then I ask it to produce the rationale. So for example, the answer is 42, the human says, and then the model generates the reasoning, and then you can fine-tune the model on, again, the problem, rationale, and the answer, but don't show it the hint as if it was solved directly. So this helps you expand the training set to include more difficult problems now. So basically, it allows you to bootstrap the reasoning capabilities and not just say limited to easy problems that the model could solve earlier, but like now you can bootstrap it iteratively. So you basically generate reasoning attempts. You learn from successful reasoning paths where the quality of the reasoning paths is entirely based on things being correct. And for failed attempts, you're basically rationalizing them by saying, okay, here is a hint. please generate the rationale. And then you're using these generated rationales as the training data. So that's basically the algorithm that they use in STAR. It's a very bare bones and like you can almost call it an off-policy reinforcement learning technique. It's a very bare bones way of producing reasoning techniques in a model. And the assumption that is being made in this particular case is that how do you know something is a good rationale? They're assuming that if the model output is correct, which in math, they found that that was generally true, the correctness of the final output is a proxy for the reasoning quality. And so they're filtering incorrect answers. Basically, they're assuming that that will be filtering out lower quality reasoning chains, but there might be scenarios where they're not learning from incorrect reasoning chains as a result. But they get higher quality training data. And then the second bit is that they assume that the language model can generate valid reasoning paths when it's given the answer as a hint. So it kind of assumes that if I show the model the answer and then ask it to show its work, it will be able to do so. And then finally, there is some amount of assumption that the initial language model is strong enough to bootstrap from few short examples. So if the class of problems is way outside the capability of the initial language model, then it will not make much progress on this. And this is where the iterative aspect starts to become important. I was seeing a couple of hands, so let's take them one by one.
Yeah, I was just wondering, so do they start with like a math data set that has like the correct answer? It just doesn't have reasoning, right? Like that's how they know what the correct answer is.
Yes.
Okay. Because I was like, how do they know the correct answer?
Yeah, everyone is starting with a benchmark, basically, yes.
Yes. Is there filtering that happens for step 3? Are we worried that we get like the correct solution and then there's like issues in the reasoning just to like get to that solution?
So they actually don't filter in step 3, but there are follow-on papers that do filter in step 3. I mean, you can do some sort of process reward model on top of the reasoning chains and then say which of the steps make sense or which of the steps don't make sense. But this particular paper was one of the first. I mean, one of the attempts in this class is to show you papers as they evolved as opposed to like, what's the latest paper here. But yes, you can, that might be another project idea of like, how do you evaluate the quality of the reasoning chains if you don't want to depend on just the final outcome as the proxy for correctness. Yes.
What if some problems too difficult that if you tell it fails as a path, even if you tell the model the correct answer, it has been not figured out because it's just too complicated to resolve.
That's a great question. So as I told you in step 4, the assumption is being made that the benchmark on which this is being done is essentially where the problem is not too difficult. It is within range, or some subset of the problems are within range of the language model. And typically you can, so that is an assumption that is made. And then when you do iteratively, the model might get better at a certain point that it can start handling these other problems.
Another question I have is in step 3. So in the NLP, like very old literature, there's a thing called negative sum. Basically means that you or whatever is that direction. So I'm just wondering, is there possibilities that you know from the step 2 you know what's well, and in the step 3 you know what doesn't work, right? And you just use the step 2 as a positive example and step 3 as a negative.
So that's a great point. Let's come back to that one. So I think what I'll show you by the end of the lecture is that learning from negative examples has not been nailed. Learning from positive examples has been, like if you have any non-zero reward, then you have an ability to close the RL loop, which is not happening, close the reinforcement learning loop, which is not happening yet in this particular set of examples. So you do need to be able to close the loop in some way. So if you have negative examples, there are some papers that have tried to learn from it, but like that's not something we'll cover today. Yes.
I have a similar question, like how to evaluate or verify the quality of the generated rationales on this failed attempts after giving the hints. Like since the model already knows the answer, but it might generate like a incorrect reasoning that leads to the answer.
So that's a great problem. So you're saying that in step 2 it might, or in step 3 it might generate wrong rationales, is what you're saying? then it will learn wrong reasoning from correct attempts. Yes, that will be a problem. In this particular case, they don't have any further filtering on top of rationales. So there will be no way to hill climb in that case. You can have humans look at the reasoning chains. It could be tedious, yes. Okay, so going through this in a little bit more rigorous detail. So you start with a prompt data set where you have the questions, the rationales, and the answers. This prompt data set will be small and compared to the amount of data that we want to train on. For example, this is the multiple choice questions where you put your grapes just before checking out. There's a rationale, and then the correct answer is, for example, B, which is grocery cart. Now, you have a training data set which is quite large of examples that have questions and answers. This would be, say, if you have a benchmark, you might have a train subset of the benchmark and a test subset of the benchmark. And what vanilla star will do is it will start with this rationale data set and training data set. So it will first few shot prompt the model with the rationales in the rationale data set, and then it will get the model to produce the rationales and the correct output. And then, so this is on the training data set. So now it's few shot prompting, but it's supplying questions from the training data set, and it's checking if the answers are correct by the language model. And it will collect these set of rationales that it can use. If they and then it can fine-tune the language model on these correct solutions. If you have rationalization, which is what star does, if the answer is incorrect, what you will do is you will add hint. So you'll be saying, okay, here is the correct answer. And you will essentially generate the rationale by looking at this hint, and then you will use that to add to that data set of rationales that led to the correct answer, and then you can fine-tune on top of that language model. And so you basically have these two sets of rationales that then you can fine-tune on top of this language model, and you can do this process iteratively. So you don't do it just once, you fine-tune it. Now the language model perhaps is able to produce better reasoning chains, so now you can again start with your training data set, and whatever was not correct, you can redo this process. So their experiments were on a small model, which is an open source of GPT-3, a 6 billion parameter model called GPT-J. They had a pretty small warm-up, and then they kept a constant learning rate, and then they basically had certain number of iterations of the outer loop, and then they increased the inner loop, the number of steps in the inner loop on each step. So one of the comments the paper makes is that they want to have a slower start in the training time, and then they want to slowly increase the number of things that are happening in the inner loop. The data sets that they tried this on was GSM-8K. So GSM-8K is just math problems that you have seen where you're basically asking, this is grade school math problems, there are about 9K samples. Then Common Sense QA. Common Sense QA is essentially problems that you would see on, say, related to day-to-day stuff. So you will have these multiple choice questions, and then you have these answers, and there's rationalization that looks like this. And then arithmetic problems, which basically was some sort of an addition problem on multi-digit addition. So they generated, the last one was synthetic data, where they randomly, they generated some of these things themselves. So in terms of results, some of the results that stood out in this paper was that just compared to, say, supervised fine-tuning on, say, math benchmark, they could boost with this star approach to 51.7, but they only used 70 to 87% of the data in terms of so they had to throw out a whole bunch of data that did not have correct solutions. And other challenge is that it's not really true RL. So if you basically do multiple iterations of this, it starts to plateau after a while. So RL has its own set of challenges, but here it also starts to plateau. So you have to really pay attention to how many iterations you can do. And there's some amount of tweaking there that you have to do. The other interesting set of results here were that this was on common sense reasoning. So they actually looked at, this was a question that several folks asked here. They actually tried to see the rationales for common sense QA. They showed it to human raters, and they asked human raters to say how likely they are to prefer the rationales from star versus otherwise. So star-generated rationales versus the few-shot rationales in the rationale data set. They compared those, and what they found was that generally the qualitative analysis showed that their rationales were pretty reasonable. Now, common sense QA, as you remember, is a natural language, like it's tackling daily problems here. So as a result of that, the rationales seemed pretty reasonable. And then the other aspect that they noticed was that star in general require, like if you use direct fine-tuning, you basically do get a certain level of accuracy, but star with rationalization gets that accuracy, but it does not require that same, like it requires much less data compared to what you would need for fine-tuning. So rationalization helps you get to an accuracy without using, like, so 86% of the data is used, but you can basically get to the depth set accuracy of 72.5% compared to like using a lot of training data. So this was a very small model. So this was first signs of life that was shown for reasoning. In terms of mathematical reasoning, this was an interesting one on GSM-8K. What they found was that the use of rationalization actually did not improve performance. So like star by itself was not helping in this particular case. So what you see is that you have GPTJ, like basically it improves of the baselines, but it's basically not helping too much. If you directly do fine-tuning on good data, then you can actually improve it similarly. So one of the reasons that is the case is the number of calculation steps that were used by the model themselves. If you force the model to use chain of thought versus you provide these rationalization steps is actually pretty similar. So in some ways, it was not helping if the problem is too simple. Like the whole notion of like getting the model to reason if the problem is too simple was basically not helping. So GSM-8K for GPT-4o was very much within capability. So similarly for GPTJ, so there was not much improvement here relative to, but it did show that direct fine-tune versus star with rationalization, you still had some gains. Okay, so some takeaways here are that the whole notion of rationalization conditions on the fact that you have an answer and then you can essentially figure out what rationales would be good. And the outputs without rationalization are examples where the model is already quite confident, but then the model is not yet, if you can look at the answer, then in certain cases it might actually do a better job producing the rationale. And if you do few-shot prompting, you can basically really help the model in how it should produce rationale. But the style of rationale might actually influence the model in certain ways. So you do have to, like prompt engineering in this particular case might bias the model in certain ways. So effectively there are certain challenges. One challenge is that the rationalization, the quality has a certain amount of effects. And the second bit is that if you're few-shot prompting, then you are biased by how the rationales were formatted in your few-shot prompts, and that might affect what kind of rationales the model would produce and what you're training on. So overall, I think this kind of gives us a sense of just that in the model space, if you basically bootstrap the model to generate rationales, you can get high sample efficiency while not having to get humans to generate these reasoning chains. And you can apply it to many problems, like you can apply it to symbolic problems, natural language, mathematical reasoning. Some of the challenges that are there in this overall techniques is that you don't have a very good evaluation for rationales for most tasks because you basically have to have a human evaluate them, or you need some sort of a process reward model to evaluate them. There might be true negatives and false positives, so you're just filtering based on correct answers, so you might have some invalid steps in between, which might cause problems. Yes?
So this method is useful for front-end models, right? Because if you want to fine-tune a small language model, you can just use a front-end model to generate these training data, right?
I don't know how to answer that question.
So
you're saying that
you don't have to rely on a small model to generate you this new additional data automatically. You can just use a big model and it can train you stuff. But I'm wondering that the main benefit, I mean, you are actually getting training out from nothing. What is shows when you are training something which is basically the front end.
Yes. So the goal for a lot of the work that we're discussing is the ability to, I mean, we're showing the solutions on small models, but at the end of the day, what we want to be able to do is take the model, take its outputs, and then use that to improve the model. You can always take a more powerful model and use its outputs, and that's like distillation process.
Yeah, that's clear. I mean the theory,
Yes.
the
Yes.
attempt is clear, but I mean when it comes to practical application,
Yes.
so I will use this method when I'm at OpenAI or entropy, and I'm training the next 1 trillion parameter model, and I need additional data beyond what I have already.
But that's a fair point. Or you want to basically improve the model on certain set of capabilities that they actually don't have, they won't produce good model outcomes on.
So what I mean is that, so if I want to improve the performance of a 7 billion
Yes,
model,
in practice,
then
yeah.
I wouldn't use this because
Yes.
I get high quality data from distillation.
Yes.
Frontier models much
Yes.
easier.
We are not covering distillation, but that's a fair point.
Okay, thank you. Just one.
No, that's a fair point that you can use one of the frontier models and distill things, but this is more an attempt to build it from scratch. And for you folks to understand what might that take. Yes.
I'm curious why this isn't like full-fledged RL, and also whether.
You're leading me to my next slide.
Oh, okay, great. Oh, and also I'm also curious. So, like, when you would decide to make the choice of to post-train with SFT versus RL, if there's any different implications of how much data or compute is needed.
Hold that question until the end. But I'm covering that. That's part of the lecture. So just to cover, so in STAR, you basically were just using the correct output, which is like a proxy for a verifier where like you already know the answer. If you basically also add a verifier in that whole loop, then that would be called VSTAR. So there was a paper that basically had a generator and a verifier training in a loop. And then Quiet Star was essentially adding an internal thinking. So what it was doing was essentially, instead of having reasoning steps be in the language space, it was actually putting reasoning steps in the latent space with MLPs. So why have them in English when you can have the model thinking internally? So before I move further, actually there have been a lot of questions, so I'll only pick one of these questions, but let's look at question 2. What bounds the performance of STAR as an approach? You can talk to someone for a minute and then let's chat as a class. Let's come on back as a class. So what performance, like what bounds the performance of STAR as a technique? Any takers for that?
Like multiplication equations, so maybe it helps on conversion.
I'm seeing no hands, you guys are talking. All answers are welcome. No without. Yes.
I think this is kind of like a silly answer. We were thinking like there are some logical steps that are kind of more complex than others, and you wouldn't expect STAR to be able to make any logical leaps that are not in its training data set, right? Like the rationalization should all kind of be of the same level as what it was trained on. Just this allows it to get like more rationalization data. That's right.
Okay. Okay. So it will not make. I mean, it will basically not have a logical leap into, say, new domains that will have figured out new things, is what you're saying. Okay? Any other takers?
Absolutely, you can believe applies the capability of the model to do like the recognition, because like if the model is really bad at like creating new logistic reasoning, it will introduce wrong samples into the training and like overall it will increase its.
Say that loudly, what you're saying.
Yeah, so we just think like this performance is intuitively dominated by the by models' capability to do reasoning because
I see.
because
So if the model can't reason even given the hints, then it's also not going to work out because the rationalization won't show up at all.
using wrong samples into the data.
That opens the question, what leads to reasoning in the base model?
I think some answers make it inherently easier to rationalize than others. For example, if the final answer is like 225, you probably know that at some point there's like the multiplication of 15 and 15 or something similar to that. But maybe some other numbers are not as straightforward. And I also think that if there's a lot of problems that you don't know the answer to and that forces you to rationalize, then it probably you probably need more data so that you can form more generalized reasoning to backtrack.
Okay. I mean, that is in the right direction, yes. Okay. I think all of these answers are fairly valid, but I think this is worth keeping in the back of your mind as you move into RL because a lot of the magic in this particular domain is like, what can the base model do as we're building on top of that? So we'll come back to that. Okay, so the second paper that we'll cover is DeepSeekMath that will focus on mathematical reasoning. And it will actually use a form of RL that it proposed that has become quite popular. So we already looked at this graph earlier where we were basically showing that in math domain, if you do train time scaling, you can do much better. And okay, so what this slide is showing is that if you look at the performance, so this is an earlier benchmark than AIME. It's actually a simpler benchmark than AIME. It's called math benchmark, and you're basically looking at top at 1 accuracy. So if you look at the date of the benchmark, you'll see that as the model size is increased, typically the accuracy on this benchmark has gone up, but then suddenly when DeepSeekMath came out, a 7B model was doing really well. And the main leap that they made was that they were able to do the reinforcement learning part with just in the train time scaling loop correctly. So we will see what led to that innovation. So the first thing that they got right was that typically when you try to improve on math, and this was something that was done on top of PaLM as a paper, PaLM model, there was this paper called Minerva, which improved PaLM model on STEM. And what they did was they trained on a lot of science and math data, typically like archive data. What DeepSeek did was it was like, okay, actually, training on archive papers is not the trick. They actually trained on common crawl web pages, but they started with a DeepSeek coder model. So they said that if you start with a model that has already been improved on code reasoning, then it will actually do better. And then they did a really good job at curating from content from common crawl pages on math. And they found that often archive papers in some ways don't have adequate amount of math content that would give us coverage. So Open Web Math, by curating that and mining it, they were able to actually, and getting better coverage across math domains, they were actually able to get much larger yield in number of tokens. And that was their first exercise in like priming the model before they take it to RL. So this was related to one of the comments that were made, that if the model is not strong in a certain domain, you do have to improve its capability in that domain. So this is that step. So they basically got coverage across a lot of math domains, showed a lot of high quality data in math, and they started from a code pre-trained model. And so they actually showed that archive training was actually not really helping, but code to math significantly helped because it allowed the model to reason better, do tool use better. This was actually the first time that this was shown that like a model, if you start from a coding-based model, you could do better. And then the other thing that they showed was that the curation of data really helped in this particular case. Now, the second step that they did was, okay, now that you have like you've trained the model on math using supervised fine-tuning, what do you do next? So they actually scale up their RL. Now, the typical RL algorithm that has been used in RL for human feedback, even with verifiers, is called PPO. So you have to keep your policy and your new policy. So you basically, this ends up being a memory problem if you try to do it on larger models. A 7B model is fine, but if you try to scale up RL, you have to keep multiple policy models, and then you also have to learn a critic model and a reward model. So typically in the RL loop, you have an old policy, a new policy that you're learning, you have a critic that's basically giving feedback, and then you have a reward model that's assigning the rewards. So keeping all 4 of the copies of models starts to become challenging. So what they did was they proposed a new technique called GRPO, where instead of having a critic or a value function estimate things, they basically use some sort of a generalized advantage estimation that I'll show you in the next slide. And then you only have 3 copies of the model. So now the PPO, which needed a lot more memory, instead of that, GRPO essentially could use just a group for the baseline. And the way that works is that for each question, you sample a lot of the answers, and then you score them, and you normalize the reward. So this is the score that you gave for each of the answers using the reward model, and then you normalize the reward as reward minus mean of rewards divided by standard deviation, and then this becomes your advantage, basically. So typically, if you look at the way DPO works or all of those techniques works, you're basically going to compare the rewards. So by doing a reward minus mean of rewards divided by standard deviation, you're effectively providing a comparative technique across rewards. And so the reason this made sense was because reward models are going to essentially be trained on comparisons anyway. So by providing the grip context, you can save memory, and now you can start scaling up RL. And your advantage function in this particular case is essentially, so I didn't add the full formula because I just wanted you guys to have intuition. You could just like take the reward, subtract the average reward, and then divide that by the spread of rewards, and you can get an estimate of the advantage. And on math, they were able to go from 46.8 to 51.7, and this was actually the first open source model at 7B scale that crossed like 50% without having a critic. This is a much earlier paper, but then this gives you a sense of the technique that they used. And further, what they showed was that if you look at different variants of RL, effectively what you are changing is either the data source, so I showed you how they curated their data, and then you're deciding how to compute the gradients. The gradient depends on gradient coefficient and the probability of the output given the question. So the gradient coefficient computation changes in different algorithms. So their estimate of gradient coefficient was coming from this group estimate or group baseline, which worked well for a single step problem where you're just trying to get the answer. So if you compare approaches like STAR, where you basically are just generating things once, and if you get correct one, you basically get a reward of 1 if it's correct and 0 if it's wrong. Or if you do online rejection fine-tuning, you are still generating things online, but you only get a reward of 1 if it's correct and 0 if it's wrong. So you basically reject anything that is incorrect. GRPO is generating rewards online with the reward model, but it's basically getting an advantage function because you're doing multiple samples, and then you're giving them a score, and then the advantage for that score comes from this group baseline by computing the mean and then dividing it by the spread of rewards. So now you can ask me the question that you were asking me earlier about the difficulty of the problems.
The difficulty of the problem that I make regression on simpler questions.
Mm-hmm.
Yes. So I'm curious if you are updating the model with fine tuning for difficult questions, you are essentially updating all the weights. So isn't that going to potentially, theoretically, have any regression on simpler questions or other benchmarks?
So this is the table I wanted to show you. So effectively, if you're basically trying to close the loop, what you're trying to figure out is how much reward you are giving. So simple problems effectively might equate to you're going to get a reward of 1 anyways, and you're like never getting a reward of 0. And with GRPO, you're getting some form of a distribution of rewards that I was showing here. So if you don't have any distribution in rewards, then so effectively what you want is some form of a distribution of rewards across the set of problems you are showing. If there is not a distribution of rewards, there's nothing for the model to learn. Like if all the rewards are 0 or all the rewards are 1, then basically the normalization doesn't work. Does that make sense?
Yes, but
Which we will solve in the next, the shortcoming of this particular method we will solve in the next paper.
But this reward is specific to like this one particular feature that we're trying to train, and not like the basic overall holistic benchmark that we trained for the previous model before.
So, I mean, it's basically taking problems and then computing answers, right? if across the model you basically are showing problems that are all very hard, then the model has no capacity to learn because it will basically have no reward at any point.
I see. Right.
It needs some hill climbing signal, right? Like, I'm not showing you a formula, I'm intuitively explaining it to you. Yes.
Yeah, actually, I just want to comment on that piece quickly. I think my interpretation of actually the solution to that is like in the original paper is like in DPO, that's why there's a KL divergence term. So essentially it's like, it is a valid concern, I think, because it's like, if we're updating the weights, we could probably stray really far from like the model. And maybe we can get really good at answering these benchmarks, but if we got the model to be really optimized on all these like simple benchmarks earlier, like we're straight away. So I think in addition to the normalized rewards, we also have some like KL divergence and penalty and policy optimizations.
Okay, that's a fair interpretation. That you add KL divergence and then you don't deviate from what it could already solve. Okay. Yeah, I was interpreting it more along the lines of like, how do you have good distribution of problems so that the model has the right hill climbing signal? But I think what you're saying is that if the model could already solve something, then KL divergence solves that part of the problem. Okay, thank you.
Right. Just a question is like, so if you were trying to post-train so that it has like a new feature, do you really have to update all the weights? Or
No, I don't think so, right? I mean, there have been some more recent works that have shown, there are some blog posts that have been recently shown that like you can do with like LoRa updates and so on. So I do think that either KL divergence or some like subset of features could solve that problem. I think the reason this is interesting is that you want perhaps that these kind of techniques allow you to improve the model overall. Yeah. More questions?
I have a question. Yeah, rationalizer just have a multi-PV down level, right? Whether it's 0 or 1, but for this one you have a score. How do you come up with a continuous score?
How do you come up with a clean score?
Continuous score.
Oh, because you train a reward model, right? I mean, you can also have zeros and ones there, and then you can average things, but...
So 0, 1, like they have a continuous score, but they have a threshold, so they get 0 and 1.
No, so what I was showing you, you are training a reward model that is basically going to give you a score for that feedback. Yeah. If you only use 0 and 1, that can be a proxy, but then you can do some averaging. Okay? So what this roughly tells you is that if you do basically the online reinforcement learning loop and you sample from the current model, that beats what we were doing earlier. We were in star approach. So overall, what they showed was that you can improve the majority of the, like if they had 32 tries, it was improving the majority at K, but it was actually not improving pass at K. So if you were basically looking and plotting pass at K, say 1 is correct if you sample 32 times, then that was not what was improving in their paper. What was improving was that majority of the solutions become correct. That's what was improving in this particular paper. So the model actually became more consistent, not fundamentally smarter, was what they showed. Now we'll cover the last paper called DAPO, which is basically going to fix some of the problems with respect to reasoning on harder problems. So if you naively scale up GRPO and want to do this on even a Qwen32B model, which is very easily accessible, and you would get 30% on AIME benchmark. And here I will show you a lot of technical terms, but I will try to explain to you intuitively. Some of the challenges in just doing this on Qwen32B ends up being like the entropy of the model collapses, the model can become too confident, the training can become unstable, and the response length, the model output length, can become uncontrollable, like it can explode uncontrollably. But DeepSeek did get 47% on AIME, like the DeepSeek R1 paper did get 47%. So DAPO, as a published piece of work, tries to make explicit what were the techniques in RL that were not covered in, say, GRPO. So some of the techniques that they talk about is that in PPO you have to do, so you're basically trying to do some sort of exploration in your standard PPO algorithm, and the standard PPO clipping treats the increasing and the decreasing on that very similar. So basically, if you have a low probability token, it can only hill climb so much, and then the high probability token can also get clipped, so the exploration can collapse. So basically the clipping function in the PPO algorithm needs to be asymmetric, and that will allow bigger increases. So that was the first thing that DAPO found. In terms of graphs, what that roughly meant was that if you did clipping, then your accuracy was much better, and if you didn't if you could allow clipping higher, if you could allow asymmetric clipping, the purple plot shows you that you could achieve much higher accuracy, and your entropy on the right side stayed more stable and did not collapse, while if you did have, did I invert that? So this is higher accuracy, and then the entropy is looking nicer, and then if you did not do asymmetric clipping, then your entropy has collapsed. So entropy is a proxy for how much exploration is possible in the model. A second very interesting technique, which actually relates to what we were talking about earlier, was something called as dynamic sampling. So what I showed you for GRPO was that, okay, you go and sample 64 solutions, and then you come up with a distribution on them, and then you take a group baseline. What DAPO said was, okay, well, how about we oversample? How about we don't just use 64 samples? How about we oversample? And then what we want is that we will filter out things that have zeros and 0 reward and 1 reward, so that what we want is basically a nice distribution, so that most of the solutions have some sort of a signal. So they filter out all correct and all wrong groups, and they keep only some subset between 0 and 64. So they're basically doing dynamic sampling because they don't want to waste their gradient. Your advantage should not be 0. Like if you're basically your rewards are all correct or all wrong, then those groups are filtered out, and you essentially want to keep only those groups that have some signal. So this maintains an effective batch size, because in RL, if you have effective batch size for propagating the gradients, because you're not computing gradients from all correct and all wrong anyways. Questions?
That's group dependent program. One group just needs one question.
One question. Yes. So you have a batch of questions when you are training, and then you're filtering out questions. Yeah.
It seems 64 examples is quite small. I'm wondering if it's because there's very limited amount of AIME questions out there, and whether that was enough.
So this is more an exemplar here. You can choose how many samples you pick, but at the end of the day, this is mostly to showcase what was possible from their paper. So AIME, yeah, this will be benchmark specific, and the difficulty of the benchmark and the capability of the base model. And I think the third bit that is worth noting is that the reasoning chains have certain amount of length. That matters. So if you are basically doing a sample level loss, sample level means that for each question answer pair, that sequence you're computing a loss, then each answer is basically counted globally. So in certain cases, if you have a very long garbage answer in the model output, then that basically gets same weight as a short good answer. So they effectively suggest that you should have some sort of effectively length penalty, which should put better, they want to shape based on the length. So they put a token-based loss as opposed to putting a sample level loss, and that they gave them some gain. And in particular, what they were controlling for is both the entropy and the mean response length. So effectively, if they didn't have a token level loss, they were noticing that the entropy was growing, and the response length was also not looking like it was growing uncontrollably. So they wanted to shape that better by putting some form of a penalty there. So they put token level loss for that. And then finally, there are certain cases in which the model encounters a hard problem. So it basically gets truncated at the end because it was thinking and it was basically producing model outputs. And these truncated reasoning chains can generate a lot of noise. So they basically put a gradual penalty in the tokens to deal with that, and that allowed the training to become stable instead of adding noise. So effectively, the generation entropy, instead of becoming unstable once the model was learning to generate the model as it progresses starts to generate longer and longer reasoning chains, and that can get truncated and that can cause problems. So there are a couple of different ways in which different papers have tried to tackle this. One is that either they increase the context length over RL loop to handle that. In this particular case, they are basically putting this penalty function so that they can handle this part. So overall, what this showed was that when you started with GRPO on this AIME benchmark, if you put overlong filtering, you went from 30 to 36 on the Quen32B model. If you did asymmetric clipping, you could go to 38. With soft overlong punishment, you could go to 41. And then with token level loss, you go to 42. And then if you do dynamic sampling, where you're basically doing a better distribution of rewards across the batch, you have a better signal propagation. You basically got to 50, which was even better than what DeepSeek R1 distilled down to Quen32B had done. So they could actually hill climb on the Quen32B themselves and get to a pretty strong score here. So some of the learnings from this paper was that the loss function by itself was not a reasonable enough proxy when you're learning in RL. You have to look at the response length, you have to look at the entropy and keep it so that it's not too low, but it's not too high either. And then the percentage of samples that have a full accuracy of 1 tells you how much you need to sample. So that's all three are important principles in learning in RL. And some of the challenges that you might have to look out for is that if your response length in the model outputs is exploding, then you have to control the loss there, you have to control the entropy, and then if you're not seeing improvement after a certain number of steps, then your reward model actually might be saturated. So effectively what this is saying is that the optimization in the RL loop is harder. So if I were to answer the question that was brought up earlier of like SFT versus RL, RL does provide you, in the domains where you do have a strong reward signal, it does provide you the ability to hill climb with fewer number of examples, but it does take a lot of work to like get it right. While supervised fine tuning, oftentimes, if you do have access to a lot of high quality data, is a faster way to just improve the model performance in certain cases, but it doesn't bring reasoning capabilities or boost them in certain ways. So if you were to compare the three different techniques that we talked about today, so if you basically only had a few different examples, like 100 examples with reasoning, and you are effectively just like playing around with a model, STAR is a pretty good, and you don't have RL infrastructure, STAR is a pretty good way for you to like start getting the model to reason. And simple reasoning tasks like GSM-8K actually will see reasonable amount of improvement there, maybe not phenomenal, but like you're still staying within what the model was capable of. If you go to DeepSeekMath and you use GRPO, you do need a good enough base model, plus like you do need to prime the model with good instruction data, but now you have a reasonably strong algorithm that can work even if you don't have enough memory, if you have a limited number of GPUs, and then for standard math reasoning tasks, this was well proven. And then if you, and you need DAPO kind of techniques when your reasoning chains will end up being longer, which typically correlates with harder problems. So if your reasoning chains are going to be much longer, you need state-of-the-art performance, then you do need to control all of these variables in your RL algorithm and infrastructure. But for competition level problems like AIME and IMO, this is very useful. So what is it that we expect to improve? All three techniques will improve in general the majority at K performance on the y-axis as you put more compute. The answer formatting in generally will improve as you apply these techniques. And in general, the model will be more coherent over multiple steps. But none of these will yet improve the fundamental capability or just teach the model to solve new problems or generalize a lot out of domain. So there is some set of questions that are being asked at this point in time. What would it take for the last part to start improving? Yes?
So that part is because I'm wondering whether it's because you just done the part like all right or all wrong, because that's, if you done that part, that's like the only way you improve on that is like on the path that A that you improve on all wrong. So you can at least one right, so the path K can improve, but because you're done all wrong wrong, you can never be wrong.
I see.
I'm just wondering that's the reason.
That's not the reason. I think the more fundamental question is that to improve pass at K, you're basically improving the fundamental capability of the model to solve new problems, right? So you want to see the model show capabilities in certain ways. So typically the fundamental capability scaling comes from, the fundamental capability step jumps have typically been seen by either some sort of a breakthrough or by scaling in some dimension.
Okay, so if in the industry you see that this thing happening like for a set of the problems always give the wrong answer, then it's possible that, I'm not sure whether it's good way to do so, but you can answer the question to some other models and get the answer and then go back to the model. So
Let's take that one offline. Okay, so one of the things that I keep highlighting is something to keep in mind is that a lot of the RL loop or even the star method, like the quality of rationale, all of that depends on the ability of the model to reason, or there needing to be some sort of a verifier or a reward model. And the reward models, if the model is too capable, then the rewards will get hacked, and if the reward model doesn't have enough signal, then you're basically not able to hill climb the loop. So it is a harder optimization problem in that perspective. We looked at last lecture, or last Friday, we looked at the autonomous coding applications where you do have access to verifiable rewards because you have, like in math and code, you have the final correct answer. Then you can also give execution feedback, which was the RLEF paper we looked at. And then you also have unit test execution. Similarly, there are some domains in which you have this kind of verification available, so it's easy for you to hill climb. But then how many such places do you have this signal available? These questions will continue to come up. So like what verification signals are good enough? And then can you use an ensemble of verifiers instead of like one single verifier to make up for the gaps of what a single verifier will provide signal on? So all of these questions are extremely important. So in terms of if you were to look at open problems in this domain, so I think this is still an active, train time scaling is an active area of research. I already highlighted this. There's a fundamental question of like, why only majority at K increases? Why does pass at K doesn't increase? A second question is that we do see in the reasoning chains things like backtracking, or the model is able to like self-evaluate, self-correct. We did show those examples early on, but are those behaviors real? Like these reasoning behaviors, are they emerging, or were they already like present and they're basically statistically becoming more prevalent? And then a third bit right now is that we don't really have very good techniques to learn from failures. There have been a few papers that have tried to learn from failures in useful ways, but currently a lot of the techniques just filter them out. Some promising directions that people continue to explore in this is along the data dimension of like how do you generate better data to train the model, along the algorithm dimensions of like how do you get the reinforcement learning to be robust to noise in the reward models, what kind of rewards should we use, and then can you combine some of the rationalization techniques that we did with in STAR with, say, the techniques that we did in DAPO. So all of those are very interesting directions that you could look into for your projects. And with that, we have a few minutes left, but let's have questions.
For like the new, like being like out of the box, like models that Anthropic and OpenAI are training, how much do you think they're still relying on just common crawl, like next token prediction, like just like raw text data, right? Like that they take from like the internet, right, or anywhere, rather than like instruction tuning data that like they generate like using reasoning techniques and techniques that we learned today. Like, what do you think is that fraction?
I see. So I think I don't think that's published for Anthropic, but I think Grok was more public. So typically the percentage of reinforcement learning versus pre-training has been closer to, I think last year it was closer to say 99%, 1%, and then it's grown to perhaps like 5% or something like that. But Grok 4 claimed that it did 50% RL, but it actually did not quite improve. 50% RL should give a big jump, but you're bottlenecked by a lot of the things that I'm showing you here of like your rewards are not strong enough, or there's noise in rewards, all of those things are going to be bottlenecks. So there's still a lot of open problems in this domain. Yeah. Let's see if there are more questions across the board. Or is this lecture too complex for people to ask questions? Too complex? Okay. Happy to answer questions after. More questions across the class? No?
I have a question. Like for the majority, if you go back to the previous page, we have the first thing majority pay as an majority pay is or not as a pay. Is this something like if the model perform okay in this calculus and you help it to perform better by RL, but if the model never sees ineligible or always fail on ineligible, regardless how well they perform on calculus, they can never import ineligible. Like that's a fundamental reason. Like class K is like fundamentally you think you need fundamentally new knowledge. And majority K is like you perform better at it.
Exactly. Yes.
Okay, so maybe that's something like that's not the reinforcement learning example, because reinforcement learning is getting better at something you already can do little.
Yeah, I mean, it's basically able to explore better in the design space of what it knows, and by exploration and search, it's able to arrive at the solution. There was a question here, which I didn't let you ask.
All right. Yeah, I was curious for, especially on the directions of data. For very unique data set like AIME or USML, where the number of data sets is very limited, how can we ensure that we have enough signals for verifiable rewards? I mean, like, there's not enough data, but we need a lot of signals. So how can you kind of like make sure that you have enough training and verification without accidentally leaking data?
So, I mean, RL is more data efficient, so you do not need that much data to begin with. So, I mean, like, that's why I was presenting these papers. You do see that a certain number of, like, enough examples is good enough to hill climb. The verification signals are more a function of, like, having good set of verifiers. So, I think I already covered the ensemble verifier paper, right? Like Weaver, she already covered that. So, it's not just a matter of having a single verifier. You can have multiple verifiers.
I see. So when there's not enough data, we can just make up for that with many more verifiers.
So I think you solve the data problem separately, but like I don't think the not enough data is the right abstraction. I think it's, do you have enough data to hill climb on is the right abstraction, right? Like where you don't end up filtering out if you were doing dynamic sampling, for example. Okay, with that we'll close the class, and I'm still around. Thanks everyone.